We'll look at a few examples of working with PD. So first, we will show that this set here entails this sentence. I've already gone and written out the members of the set as assumptions here, and our goal sentence is here at the bottom. Now the goal is universally quantified, right? This quantifier here, this is our main logical operator. So what we'll use to get it is universal introduction. So for that, what we're going to want to do is we'll write out a substitution instance of the goal sentence using a constant that doesn't appear anywhere in our assumptions. And in our assumptions, we've got this constant A. So we can't use that, right? That's in an open assumption. So we'll use B, I guess. Um, so we'll have this, and then this is going to be our next goal sentence. And because of the fact that it's got this different constant, doesn't appear in any open assumptions, we'll be able to use universal introduction on it uh, to get our final goal. This is a conditional, so we will be able to get this using conditional introduction. So we'll set up to do that. So we'll assume FB for conditional introduction. And then we will derive SB. Okay, SB, not really clear how we're going to get that immediately. Um, Presumably it's going to involve these, but we're not going to be able to do anything with these until we go and apply universal elimination, instantiate them for B. So let's do that next. So we'll go to working top down. We'll take these and apply universal elimination. And we're going to go in and replace these variables with the constant B. So this is one universal elimination and two universal elimination. Two universal elimination. And now from here, we're pretty much just working with SD rules, right? So if we go back to the goal sentence here, and then we look at what we have at the top, right? So we can get SB from, if we could get IB and SB, we could get SB by conditional elimination. We could get IB and SB if we had HB by conditional elimination. We could get HB if we had FB or GB. Oh, whoops, that's supposed to be there. But actually, this would also be, we'd also be getting the HB by conditional elimination. So that was, in fact, right. And then the FB or GB, we can actually get that directly from 4 by or introduction. So by doing that, we can go through and just delete these rows that we don't need. And we've joined up the top and bottom of the derivation. So all that's left is to fill in the line numbers, put in scope lines, and this whole thing is done. So next, we'll look at this derivation. We'll show that this set containing this one sentence entails this. Now here, our goal sentence is a conditional. So we're going to use conditional introduction. So we'll assume there is an XFX as an assumption for conditional introduction. And then we will derive there is an X GX. Okay. Now, looking at this goal sentence down here, this is an existentially quantified sentence. So the first thing that you would probably think is that we would derive it by existential introduction. So we derive this for some constant, any constant at all, and then use existential introduction on that. There are no constants anywhere in our assumptions, so let's just assume that we're going to get it by some arbitrary constant. So we'll just suppose A. So now then this A here would become our new goal sentence. Um, okay, so how are we going to get this? Well, that's not really clear. I mean, it's just an atomic sentence, right? Not really clear how we're going to get that. So we can go to working top down. We can use universal uh, elimination to instantiate this here for A. So that's one universal elimination. Now, well, we need to get FA. And the only real possibility here for doing that would be to work with this. So we're going to need to use existential elimination, it seems. So we'll introduce a new subderivation and set that up for existential elimination. So we'll assume FA for existential elimination. Um, then here we can use conditional elimination to get GA from 3 and 4. Then we're going to run into a problem because the A here, this is the constant that we introduced in this assumption, which means that existential elimination won't allow us to pull it out of this subderivation. Like we can't actually use existential elimination to get the GA out of here. So that's not going to work, right? Deriving GA inside the subderivation isn't actually going to work. Um, Another possibility would be we could try using existential elimination on a different constant. So let's say we tried introducing B here instead. And then we'll try to derive GA inside here and pull that out. But see, here we're going to run into the problem that what we have to work with at this point is FB, and if FA, then GA. Um, and I mean, like that, there's nothing we can derive from that, right? The conditional, we can't get anything here by conditional elimination, right? The antecedent, um, like this does not match up with the antecedent of this. So we can't get anything there by conditional elimination. There are no inferences that we can make from these. We could instantiate this for B, get if FB, then GB, but then we're going to run into exactly the same problem we had before. We can't pull the GB out. Um, so what we're actually going to have to do here is just rethink this initial strategy that we started off way down here, where we were going to derive there is an xgx from GA. What we're actually going to need to do is we can still leave this here, this if FA then GA, but we're going to need to derive this by existential elimination. What we can do is assume FA for existential elimination again, and then derive this inside the existential elimination subderivation, and then pull it out with that, because this doesn't contain A in it. So doing that is fine. So then inside this subderivation, we will get GA by lines 3 and 4. This is 3 and 4 conditional elimination. Then this is line 6. This is 5 existential introduction. And then we can pull this out of this subderivation with existential elimination. It's lines 2 and then 4 to 6. And then we just need to fill in the line numbers here. for this. This is lines 2 to 7, conditional introduction. Um, the moral of the story is that existential elimination has the tightest restrictions of any of the rules in PD, which means that quite a lot of the time you need to use it as soon as possible and let it structure the way that you're going to do your derivation, because of the fact that its restrictions are so tight that it's going to force you to do things in particular ways. And the other rules, they have looser restrictions, which means that they can adapt to what accidental elimination is forcing you to do.